Assalamu alaikum dear students. Hello everyone, welcome back to Learn Daily Physics. So we've described in a previous lecture we've described a relation for lambda d, and we've seen that lambda d is equals to under root epsilon naught kbt over n infinity or n naught we've said is into e square. So in our today's lecture we are going to find a relation between that when the particle is inside, what is the value of Debye potential here. We are going to calculate the Debye potential today in our lecture 5, but before going toward this we have to understand what Debye sphere is. So first we will discuss what Debye sphere is, then we will calculate the Debye potential, and we will see the three cases of Debye potential: that when particle is inside the sphere, when particle is outside the sphere, and when particle is on the boundary. So let's see what Debye sphere is. So Debye corresponding to the Debye sphere corresponding to the Debye length, that this is the Debye length, and with this length when we got a sphere, it is a common sphere, but whose radius is equals to lambda d, and we know that lambda d is equals to this term. So particle inside the Debye spheres are negligible effect on the particle outside the sphere. Here we have some kind of particles. For example, this is positive 1, and we have some kind of negative particles, or you can say positive particles here. It's better to say positive particles because we have negative particles which is making the cloud around these positive particles formed. So let's say we have a positive particle inside. We will prove next, we are going to prove this, that the potential for this particle on the electric field from this particle will be 0 for a particle outside this sphere. So the sphere has negligible effect on the particle outside the sphere. This sphere will have 0 potential here, and this sphere will have 0 electric field here outside the sphere. We will prove next. Okay, after this we are going to prove this when we will drive the Debye potential. So volume is equals to 4 by 3 pi r cube. We know that the volume of a sphere is equals to 4 by 3 pi r cube, and V is equals to 4 by 3 pi lambda d cube, and nd is here n is equals to number of particles per unit volume. When n is equals to number of particles per unit volume, then you can see that this was the volume, and this is the number of particles per unit volume. This volume could be cancelled by this one. Let's say this is n is equals to some numbers divided by volume. This volume could be cancelled out with this volume, and volume cutted by volume is equals to number is equals to the number. So this is the Debye number of particles in the Debye sphere. So nd is equals to 4 by 3 pi lambda d cube. When we multiply the volume here, this whole volume, we get the number of particles, nd the number of particles present in this Debye sphere, and lambda is equals to this term. From this we can conclude that lambda d is directly proportional to the under root of t, and lambda d is inversely proportional to the 1 over n infinity. So this was a term, but we have to understand what Debye sphere is. It was quite simple. So let's move on toward Debye potential. What is Debye potential? Our last topic we've left was 1 over lambda d square. If you look in our last topic, so 1 over lambda d square was equals to e square and infinity over epsilon naught kb t. It was an infinity or it was n naught. There's no big deal about it. It's just a representation, and the equation where I derived it was del square of phi was equals to 1 over lambda t square of phi. So if you don't even seen this before, you have to see my first lecture of Debye shielding, and then you will get that where this equation came from. So now I'm taking this term toward left, and del square of phi minus 1 over lambda d phi is equals to 0. From this I will take phi constant, del square minus 1 over lambda d phi is taken constant here, and this term will be equal to 0. So del square, this will make a characteristic equation, let's say d square minus 1 over lambda here square and square 1 over lambda d square equal to 0. So lambda square will be equals to 1 over lambda d square. This will give that d will be equals to 1 over lambda d plus minus 1 over lambda d with the plus and minus sign. So this was our characteristic equation. We can say that this is our characteristic equation. So now for this characteristic we have an auxiliary equation. If you auxiliary equation, you might have studied partial differential equations, ordinary differential equation. This term I'm using here, characteristic equations and the auxiliary equations. These are, for these you must understand the ordinary differential equations. What are ordinary differential equation? For there we have 8 to 9 characteristic equations, and the auxiliary equations we have to understand them before. So I might try that you might understand from this, but we are writing an auxiliary equation for the above characteristic equation. So auxiliary equation here will be equal that with function phi here. So phi will be equal to phi naught. Phi will be equals to phi of phi naught here, and e power minus x, because here it was del partial by partial x over lambda, this lambda d positive one. I've taken positive one, and I'm not taking the negative one because this lambda d is the distance, and distance could not negative. Lambda d will be always, lambda d will always positive, okay, will always be positive. So this is the value for phi is equals to phi naught e power minus x over lambda d. So let's see that what is this phi naught. Phi naught is the Coulomb potential here. So dB potential is equals to the Coulomb potential kq over r into e power minus x over lambda d. Okay, now this term is equals to this. Okay, so let's say that we have our first case when this particle here is here. Okay, x is here, and let's say that from this we say that here it is x. Okay, our particle is lying outside. You can make it further away from here, but I'm making it here, you can understand. This particle is here, x is outside the sphere. Let's see when x is greater than lambda d, is much greater than lambda d, it is here, or you can say far from this sphere, x is greater than lambda d, then what will be the case for this potential? Let's see. this is our case 1. Case 1, when x is greater than lambda d, that the particle is lying outside the sphere. So here you can say that you say x is so large that x approaches to infinity. Here its value is so large, it's too large, then phi will be equals to phi naught, this is a naught, big naught, e power minus infinity. You can say e power minus infinity, and phi is equals to phi naught over e power infinity, and it equals to 0. E power infinity equals to infinity, 1 over infinity equals to 0. So you can say that the phi here, the Debye potential outside the sphere, when this x was outside the sphere, x was greater than this lambda d, then the value of this potential is 0. So we know that E is equals to partial negative of partial phi by partial r, you can say, and this term will be 0 and this whole term will be 0. So you can say that the electric field generated from this is also equal to 0. So this was the relation. We already discussed that these charges, these negative charges will surround this positive one, and when they will surround this positive charge, the electric field from the electric field coming from this positive charge cannot come out, because it will be shielded out because of this. And if the value of this E or this phi is 0, we can say that our Debye shielding is perfect. We have perfect Debye shielding. In our previous lecture for the Debye shielding, we already discussed that what is perfect Debye shielding, when the Debye shielding is perfect and when the Debye shielding is not. When this value equals to 0, we have our perfect Debye shielding, that this positive ion have no impact or no effect on a particle placing here. A particle placed here don't know that there is some kind of particle inside this sphere, because it is not having any interaction. Because of it, it is not making any messages. No field, no interaction, no knowing of each other. Okay, so let's move on toward our second case. In our second case, we see that this particle is inside the this particle is lying inside the, let's say that this particle here is lying, x is lying here, and now you can see lambda d is greater than x. So for this case number 2, now for the case number 2, when lambda d is much greater than x d, or x, it was simply x, not xt. So this time x will approach to 0. X is so small, we have an assumption that x is so small that it approaches to 0. When it approaches to 0, we know that phi is equals to phi naught e power minus x over lambda d. When this term will approach to 0, then phi will be equals to phi naught. It means that when the particle is inside the sphere, it will experience a potential which is Coulomb potential, which is simply the Coulomb potential. The Coulomb potential, Coulomb's law, positive charges experience force which is equal to the product of their charge, magnitude of their charge, and inversely proportional to the square of their distance. Okay, so F, from that F we can calculate the potential. So this is what Coulomb potential. Now we have our third and last case, that when X is lying here, when X is lying on the boundary, when the X is lying on the boundary, what will happen? When lambda is equals to X, this is the case where lambda and X will be equal. So our case 3, when lambda t is equals to X. Okay, so here lambda d is equals to X, writing the relation for the phi is equals to phi not e power minus X over lambda d is equals to X. Then we can write it X is cancelled out and it will be equal to minus phi over, it will be e power minus 1, and we can write e power minus 1 in denominator, e here exponential here. So this equation tells us that when you move at the boundary, when you let's say you have this sphere here and it have a certain boundary like this, and this boundary here won't be like this, it will be in regions, it have some region. Let's say it is the region clouds, the electronic cloud is present in this region, and this is the Debye length. Debye length ranges from here to here. This is a cloud, this is a strip of those clouds which are shielding this, the effect of this ion. So this equation tells us that when you are inside, you have a Coulomb potential phi naught, you have a Coulomb potential phi naught. When you move outside here, you have phi equals to 0, phi equals to 0. What is the reason? When the particle reaches this, it have an exponential drop. This equation tells us that when the particle reaches here at the boundary, it has an exponential drop. It is a discontinuous. You can say that the function is discontinuous. It has an abrupt change. It has a maximal phi naught value here, but when it reaches here, it goes on decreasing. A rapid decrease occurs here because of this exponential term. A rapid decrease in this term causes it to be 0 outside the sphere. Here it was maximum, and going here it was 0. What happens here? This exponential term drops whole the term phi naught into 0 outside the sphere. So from moving this here to here, it maximum to nothing. Okay, so this case 3 equation tells us that the phi is decreased by the exponential term e, and this was the whole reason for that, this equation, you understand. So our today's lecture is over now, and thank you very much for your time. If you have any question, you can ask me on comments and comment section, in the comment section, and you can also visit on Google that www, you can write www.learndailyphysics, learn daily physics.com. You can visit this on Google, where you can have a lot of blogs, you can have a lot of books there. And the one thing I forgot to mention, that you can have the relative books. And for this lecture, for my previous lectures, Charles Kittle's Plasma, a lot of books about the topics, about all of your topics. If you're studying physics, you're doing MSc or in physics, you're doing BSc in physics, you're doing BS, whatever you're doing, you can find all of your books related to this on our site. Okay, so thank you very much for your time and assalamu alaikum.